Dear students, today we will talk about Helmholtz resonator. In the previous lectures, we have learnt about simple harmonic oscillator, coupled oscillators, damped oscillators, and forced oscillators. While doing the analysis of forced oscillators, we came across a term called resonance. And what is it? It is when the frequency of the applied force, which is a periodic force, matches the natural frequency of the oscillator. At that time, what happens? We know it already that the amplitude attains the peak value. Now, if we want a practical realization of this concept, for that we will have to turn to Helmholtz resonator or Helmholtz oscillator. What is it? It is essentially a container. It can be spherical or it can be cylindrical. It can be made of glass or of any metal. There is no binding. It is filled with air or some fluid, right? It has two openings. On one side, we can keep our air to listen to this peak value of amplitude, which is in the form of a note of sound. And on the other side, there is another opening, but it is called neck because it has certain length. So it can be spherical or cylindrical. Now, what do we do is that if we assume that the length is L of the neck, A is the area of cross section this way, right? And rho is the density of air inside the vessel. Now, what is the mass of air inside the neck only? We know that mass per unit volume is density. So mass is volume into density and volume is area into length. So for mass, we obtain a simple expression, length into area into density of air inside the vessel or the neck. Now, if we move the neck inwards, what will happen? It will decrease the volume of the vessel, that is obvious, but the pressure will increase, that is also obvious. So because there is a decrease in volume, we assign a negative sign, that change in volume is equal to area into distance. X is the distance through which, for example, we have moved the neck of the vessel. Now, I introduce a term that's called bulk modulus, right? Bulk modulus K is equal to stress by volumetric strain, right? And stress in any case is force per unit area, and force per unit area is pressure. Volumetric strain is change in volume by original volume. Now, after this, we move to the next page. And what is that? This change in pressure is equal to K times delta V by V from this expression, right? It is K times delta V by V. Now, change in pressure delta P can also be expressed as force per unit area. From this, we get an expression for force, that is area into change in pressure. Or force is for this change in pressure, we take the expression from here and force comes out to be this much. Now, an alternate way of expressing the force would be what? Simple. Force is mass into acceleration, a very common expression for it. Acceleration is expressed as the double derivative of the displacement. So, m d square x by dt square will be equal to this much, k a square x by v. Yes. For m, we will again take the value from this, that it is L a rho. So that's why we are writing it is L a rho d square x times by dt square and k a square x by v, which we have obtained from here. From here, we can rearrange to get d square x by dt square equal to this much, right? For these many terms, we write a single term mu, right? So we are placing mu for this fraction. And if we begin to compare now this equation with the original wave equation, that is d square y by dt square plus omega square y is equal to 0. You have done it many times before this. So from here you can compare that omega square is equal to k, right, or mu. And so this omega is ka times vl rho, right? So this is mu in fact. We have placed mu here. So this is Ka by VL rho. Okay. Now we know that omega is 2 pi by t and reciprocal of time is frequency. From here, it is easy to calculate the frequency that comes out to be 1 by 2 pi. Obviously, from here, for omega, we will give this value that Ka VL rho. V is of course the volume, and L is the length of the neck, and rho is the density of air inside the container. Now, velocity of sound in air is known to all of us, that it is equal to bulk modulus by density of air under root times. So once we substitute the V for this K by rho term, we get frequency or resonant frequency of the Helmholtz oscillator would be V times under root of A by V into L, where V is the volume of the container, L is the length of the neck, A is the area of cross section of the neck, and all these observables are known to us. We can always find them given the shape of container, whether it is spherical or cylindrical, and velocity of sound in air is already known to us. So that way we can calculate the resonance of a Helmholtz oscillator. What do we do essentially? Again, I'm repeating that inside this container, we can keep moving this neck inwards and outwards until at one point when the resonance is attained, we hear a peak note of sound by placing our ear near the another opening, right? So this is a simple and short concept of Helmholtz oscillator. So I'm again turning the pages, yes, so that you get a final look on the expression. Okay, so that is sufficient.